in the drone, they try to push the air downwards, isn't it?
Yeah, so
So the rover is trying to push the air downwards. Now, according to the Newton's third law, the air will also push the rotor upwards, isn't it?
yeah.
So that is what we mean by the Newton's third law. So let me just write this down. So you have to write it like this. So the blades of the rotor, they exert a downward force on the air. Now, according to the Newton's third law, which states that each force will have equal and opposite reaction, that means the air will exert an upward force on the blades. So then what will happen is, let's say if you have, if we draw the free body diagram of this particular rover, so you will have the complete weight of the object, which will be the weight of the aircraft, weight of the package, and weight of the string all combined. And then you will have the weight of the air which is being pushed up, right? So the mg will have to be balanced out by the force which is exerted by the air, and at that point we say that F is equal to mg, and we say then the net force is equal to 0, and that's why this particular rover is completely stationary. So when it states that the aircraft is hovering motionless above the ground, from here this should be a deduction that the net force is equal to 0. Getting it?
Yeah, so
Alright, so just read the third part. Let's see what could be done in this. Okay, so we have to find the value of V in this particular case, right? So what is V, by the way? So shall we see, V is the, okay, so it's given in this question stem that the air is propelled vertically downwards with the speed V, right? So air is being propelled downwards with the speed V, and this speed is what you need to find, isn't it?
yeah, so
So could you think of any mechanics formula or law or principle which can be used to find this? Just give it a minute and then we'll solve.
also I'm kind of confused.
Okay, that's no issues. Okay, so let's say if this is a little tricky, the B part is easier than this. So try to figure out the B, and then we'll go step by step, starting with A3. See if you can figure out the B part. Okay, Sheldon, so let's see how to solve this. Starting with A3, so we have to find out the value of V, right?
Yeah, sir.
And what is V? Could you tell me?
V is nothing but the velocity of the air being pushed downwards from
Correct.
the drone.
So for this particular thing, we have to use the Newton's second law. So we have force is equal to mass into acceleration, right?
Yeah, sir.
And this can also be written as F is equal to delta P by delta T. So it's the same thing. Force is rate of change of momentum. This entire thing is your Newton's second law, correct? All right, Sheldon. Hello, Sheldon, are you there?
Yeah, sir. Yeah, I
Okay.
just joined in. Yeah, sorry.
So F is equal to ma, and that can be written as delta P divided by delta T. So force is the rate of change of momentum. Do you remember this formula?
Yeah, sir. I do. I do.
Right. So now if I cross multiply delta T, I can write F into delta T, that is equal to change in the momentum. So now let's say if I draw the free body diagram again, so we had the complete weight of the object, and what was that? So we had the mass of the aircraft is 0.95, the mass of the package and the string is 0.45, so this means the total mass is 0.95 plus 0.45, that is the capital M, and the value of G can be put as 9.8. So this is the total downward force, right? So now we have to figure out what is the total upward force, F, right? Now as we have already deduced that the net force is equal to 0, so this force F, which is the force which the air is exerting on the blades, so let me write that F air. So this F air will be equal to this, isn't it?
Yeah.
So just solve for this. Tell me what is this value, 0.95 plus 0.45 multiplied by 9.8.
I'm getting it to be 13.72.
Okay, so 13.72 newtons is your value. So which means the force applied by the air on the blades, that is equal to 13.72 newtons. Now after this we have to figure out, using this we have to figure out the value of V. Alright, so now if I observe the same equation, F delta T is equal to change in the momentum. Now I will apply this equation for the air. So that means the force which is experienced by the air multiplied by delta T, that is equal to the change in the momentum. So we write that as m into V final minus V initial. Change in the momentum will be the final momentum minus the initial momentum. Did you get this step?
Yeah, sir. I did.
Now if you consider air originally as stationary, and after the blades push the air down they reach a velocity of V. So which means the initial velocity can be considered as 0 and the final velocity of the air can be considered as V. Got this step?
Yeah, sir.
So now put V initially as 0 and V final as V. And what is the mass of the air? Okay, so if you scroll up, so it states that the mass of the air pushed downwards by the blades in 1 second is 1.7. So it's just not the mass, but it's mass per second, which means the m divided by delta T, the mass per unit second, that is given to you as 1.7, isn't it?
Yeah, sir.
So from here if I write F air, that can be written as m into V and multiplied by 1.7. So basically 1.7 into V. Now Sheldon, just check if this step is clear, understandable to you, what we have done.
Yeah, sir. Yeah, it's kind of. It's actually. It's understandable.
So basically we have done, put initial velocity as 0, final velocity as V, and then put m by delta T as 1.7. So eventually we get air, the force exerted by the air, that has 1.7 V, right? So now
Yes,
Sheldon, we
sir.
have two formulas or two values for F air. In the first we got F air value as 13.72 newtons, and second we have this 1.7 V. So now all you need to do is just equate these two values. So 1.7 V, that is equal to 13.72, and now check what will be the value of V.
It's 8.07.
Yes, so 8.0, and what is after that? What comes after the 0?
07.
8.07. So let's say if I want to round this off to one decimal place, so that can be rounded off to 8.1, isn't it? So 8.1 meters per second is your answer to this question, A3. Now Sheldon, do one thing, go through this entire solution, especially for this part, and tell me if you have any issues. We'll do it again.
Alright, sir. Yeah, sir. Yeah, sir. Done.
Okay, now Sheldon, let's move to the first approach of yours. So initially you solved this question A1 and told me you had some non-zero value. So let me just do that again. So initially what you did was you had the mass of the aircraft as 0.95 and the mass of the string is 0.45, and then you check that the mass of the air is 1.7. So let's say this is 1.7, the air. So now if you check what is 0.95 plus 0.45, Sheldon,
1.4. Yeah, 1.4.
and you have 1.4 down and 1.7 up. So it appears that there is some unbalance here, but
Yeah,
this
sir.
entire principle is wrong, because here we are considering the masses. See, in a real life scenario, any object will remain stationary only when the net force on that object is equal to 0. So more than the mass, you are looking at the forces. So that's why we redraw the free body diagram. Okay, well, let me draw here only. So you will have the combined weight of the entire aircraft, and that would need to be balanced out by the force which this air is exerting on the blades. Right, so we have to deal with the forces and solve it using like we did in the previously, and not using the masses. So that's why you were getting a non-zero answer in the first part A. Remember, so Sheldon, do you remember what was your answer in part A?
Yeah, I had said something like 0.3 grams per Newton meter.
So what you did was 1.7 minus 1.4. So if you subtract these two, you will get 0.3, and you multiply that by g. So this, although you have gotten an answer, but this is zero, but this is wrong. Clearly, because if it is clearly given to you that the aircraft is hovering motionless above the surface, this is an indication that the net force on the object has to be 0. So straight away A should be put as 0. a1 should be put as 0.
Yeah, so
Understood? And let's move
yeah.
to the next part. So we have, so did you read the last part?
Yes, I did.
Okay, just a second. Okay, so it states that the package and string are now released and fall to the ground. The lift force on the aircraft remains unchanged. We have to find the initial acceleration of the aircraft. So let's draw the initial free body diagram with when the string was still attached. So what was the total downward force? So if I just scroll up, see this, the total downward force on the aircraft was this much, isn't it?
Yeah, so
So this was the complete weight of the aircraft as well as that string and the package. So that is 13.72 newtons downwards. So let me write it completely. So 0.95 plus 0.45 into g, this value comes out as 13.72 newtons. Now when I say initially the aircraft was hovering motionless, which means the total upward force, the force exerted by the air on the blades, what will be the value of this, Sheldon?
I think this would be 8 point, basically our previous answer, right? 8.02, sorry, 01.
So
Sorry, 8.1, 8.1,
8.1,
yeah.
that is the answer for velocity.
Yeah, sorry.
What we need is the force exerted by the air on the blades. What will be that value?
So wouldn't that also be
Yes,
13.72 then?
absolutely. Wonderful, good. This is what I wanted to hear. So the net upward force has to be equal to the net downward force. Only then the aircraft can hover motionless, isn't it?
Yes, sir.
So now let's read the B part. So this was your original free body diagram. What was happening? Now the package and the string are released and they fall to the ground. So the lift force on the aircraft remains unchanged, which means this 13.72 remains unchanged, and the only difference is this, the string and the package are gone. This implies this 0.45 has to vanish, isn't it? So in my
Yeah,
new
so
free body diagram, the lift force, upward lift force remains same, which is 13.72. Now the only weight will be the weight of the aircraft only, which is 0.95 into g. Now this is because the string and package are now no longer connected to the aircraft, isn't it?
yeah, so
So tell me what is 0.95 g if g is 9.8.
so that should be 9.31.
Okay. So now you have 13.72 newtons upwards and 9.31 downwards. Tell me what will be the value of net force.
That should be 4.4.
Okay, so it's 4.4. Now see, let's what we have to do for question part B. We have to find the initial acceleration of the aircraft. And so Sheldon, we have only one formula for acceleration. That's one basic formula. Acceleration is given by the Newton's second law, which is the net force, and we divide that by the mass. So in this case, net force you have found out as 4.4. Then we divide by the mass of the aircraft. And what is the mass of the aircraft? That is 0.95. Now solve for this. 4.4 divided by 0.95.
So it's 4.63.
Yes. So 4.6. And what will be the unit?
Since the F-Net's unit is like Newton, I suppose.
So what
And
is this is acceleration. What is the unit of acceleration?
meters per second, square, -1,
Yes.
sorry.
Meters per second square. Meters per second is
Oh,
the
yeah, sorry,
unit of
sorry.
velocity. For acceleration, you have meters per second square, or ms minus 2. Got it?
Yes, sir.
So Sheldon, just go through this entire solution and let me know if you have any doubts.
Yes, sir. I just read it all. I got it.
Yes, so did you write it down, the whole thing?
Yeah, sir.
Okay, great. Now let's just move on to the next question. Just a second, let me copy the question. All right. Okay, Sheldon, go through this question slowly and carefully and try to solve it.
So is this the graph for displacement?
This is
It's
force
a small
versus
down.
time. The y-axis is force, x-axis is time.
Yeah.
So it's not displacement, it's force versus time.
All right, sir. So I'm not getting the formula that we need to use for A.
See, the principle is the same. The force is equal to mass into acceleration, and which is equal to delta p
Oh,
by delta t. So use this to solve. Especially the delta p by delta t part will be useful for this question. So try it and then let me know, then we'll start discussing.
so I'm getting confused here on the A
Okay,
part.
no issues. Let's start to discuss. So see, the graph has been given, which is force versus time. Force is in newtons, so you have to observe the units first. Force is in newtons, and could you tell me the unit for time which they have given?
It's milliseconds, right?
Yes, and what is milliseconds in terms of seconds?
It's 0.1. It's the first decimal if I'm not wrong.
See, 1 milliseconds is, see, milli stands for 10 to the power of minus 3. So 1 milliseconds is this much, or we can write this as 0.001 seconds. So you have to remember this. Now let's go back
Correct,
to the
sir.
question. So it states that the tennis ball was stationary at the instant when it was hit. So we can consider the initial velocity of the ball as 0, and the mass of the tennis ball is given to us. The area under the curve is given to us. We have to find the speed of the ball as it leaves the racket. So as I said, the only basic formula which we are going to use is this: F is equal to delta P by delta T, which is your Newton's second law. Now if I cross multiply and take delta T to the left hand side, we can write F delta T, that is equal to change in the momentum. Now Sheldon, this is nothing but our impulse momentum theorem, because this parameter F delta T, so force into delta T, this is nothing but a parameter called J, which is the impulse. So impulse is equal to F delta T is equal to change in the momentum. So Sheldon, what we are doing is starting from the Newton's second law and modifying it to form this equation, right?
Yes, sir.
So now just observe in the graph. Can you tell me, is the value of the force constant or variable?
It's variable.
Yes. So that means I cannot put any value of force into this expression F, because your force is variable. So how do we approach then? So observe, the graph is force versus time, and you are supposed to find F into the product of force and time. So that means if we have to find F delta T, this would be nothing but the area under the FT graph. So let me elaborate. So let's say, let me give you an analogy first. So if we have work, so Sheldon, what is the formula for work?
Work done equals
Hmm.
well, I actually forgot. So
So let's say if you have an object, it is experiencing a force of F, and let's say the object moves ahead by a displacement S, then what do you think is the formula for work?
work done upon time taken.
No, no. So the basic formula for work is the product of force and displacement, Fs, right? So this is the basic
Yeah, so
formula for work, force multiplied by the displacement, which means if in the question, if force is given to you as a constant value, let's say 10 newtons, and displacement is given to us as 2 meters, then we do this 10 into 2 and we get the answer as 20 joules as the work done. Now we found this answer because the force was 10 newtons, it was given to us that it is constant. Now imagine a certain scenario if the applied force is variable and the particle is traveling by displacement s. So in this particular case as well, the work done will be force into displacement, but since the force is variable, there is no one value of force which can be put here, right? Because the force is variable. This is my case 2 when my applied force is variable. Did you get this?
yeah, so
So in this case, force being variable, we cannot use any one value of force, so this formula is not valid. So then how do we find the work? So the work done is still Fs, but then we write it like this. So area under the force displacement graph. So let's say if you have the graph given to you as force and displacement, and let's say the graph is like uh, just a second, Sheldon, I have to put my laptop on charge.
yeah, no worries, sir.
All right. So if the force displacement graph is given to you, let's say the graph is like this. So here you can see your force is variable. So then what do? We just find the area under this graph, and that will give you the work done in this case. Did you understand the concept?
Yes, sir.
Similarly, whenever in physics, in entire physics, if we have a formula, like for example here we have F delta T is equal to change in the momentum. Now as I told you, in any formula for physics, if one of the parameters is variable, like in this case, so in the graph it is clear that a force is variable, so then you cannot put any one value of force into it. So how do we find the value of F delta T? So F delta T would be nothing but the area under the force time graph. So now if I just scroll up, so area under the force time graph will be this, the entire thing. So technically what we should do is we have to find out the total area of this. So one method could be, we can find the area of one small square and then multiply by the number of squares inside this graph. But fortunately this particular value is given to us. Could you check what is the value of the area under the curve?
It's 0.8 Newton per second.
Newton seconds. So area
Yeah,
under the
sir.
curve is 0.84 Newton seconds. Let me write this as 0.84 Newton seconds, and this is the value of F delta T. Now to check whether the units are correct, see the parameter is F into delta T. What is the unit of force, Sheldon?
Newton.
And what is the unit of time?
It's
Yes,
seconds.
so Newton seconds will be the unit. That is indeed correct. So the area under the graph will be 0.84 Newton second. Now let's go back to our original equation, which stated that F delta T is equal to change in the momentum, right?
Yeah, sir.
So let's write this down. So F delta T you have found out as 0.84, and that will be equal to the change in the momentum. Now change in the momentum will be mass into the final velocity minus the initial velocity. Right, so delta p is just the final momentum minus the initial momentum. Did you get this?
Yeah, sir.
Now if I scroll up, what are we supposed to find? We are supposed to find the speed of the ball as it leaves the racket. This implies we have to find the final velocity. And it is given that the tennis ball was stationary initially, so the initial velocity is 0. And is the mass of the ball given to us? Yes, 5.8 into 10 to the power minus 2. So let's put all these values into our expression. So mass is 5.8 into 10 to the power minus 2. Velocity final is what we need to find. Initial velocity is 0. So Sheldon, now solve for this equation and tell me what will be the value of final velocity.
Alright, sir. So the equation is actually just 0.84 equals the mass bracket. Sorry, 0.84 equals to the impulse formula, the momentum formula, or is it just equals
See, the
5.8?
equation is J is equal to, the theorem is J is equal to F delta T is equal to change in the momentum. So we write J as 0.84. 0.84 was your area under the curve, and that you write as change in the momentum. So we write 0.84 is equal to m into v final minus v initial, which is the change in the
Alright, sir.
momentum.
Yeah, sir. Alright. Thank you. So I'm getting my answer to be 14.48.
Okay, so 14.48, yes, so approximate that to 14.5. That is your answer. So that is your, that is the
But so, okay.
yes,
No,
Sheldon.
I was just confused about the unit. I was just confused about the unit. That's all.
Unit of what?
Of the final velocity, but I figured out it's just meters per second.
See,
That's
velocity
all.
is always in meters per second, isn't it?
Yeah, sir. I just got very confused.
Okay, so now do one thing, just write down the entire solution for this. So we are starting from here. So write down all the steps.
Alright, sir.
Or rather, you can do one thing, I am actually recording this class, and later on you can go through the recording and write down the notes. Is that fine?
Yeah, so that's better.
Alright, so let's move to the next part, next sub question. And what was that? Okay, so B part is we have to find the average force exerted on the ball by the racket. So just okay, so we have to find the average force exerted on the ball by the racket. So we have to employ the same principle. The force is equal to mass into acceleration, the Newton's second law, which in turn is equal to delta p by delta t. Is this correct, Sheldon?
Yeah, sir.
So now in this case we have to find the average force exerted by the ball, and we have to show that it is close to 50 newtons. Right. Now the value of F delta t was found out in the previous question, and what was that? The area under the curve.
0.84 Newton second.
Yes. So if I just first of all cross multiply, we'll get F delta t is equal to change in the momentum. Now the 0.84 which you have, that is the area under the curve, area under the curve of this, right? So this area is equal to F delta t, and that is equal to the change in the momentum. That means if I write F delta t, that we can write that as 0.84, right?
Yeah, sir.
So since we are supposed to find the force in this case, we will write 0.84 divided by the time taken delta t. Now all you need to do is figure out what will be the time taken for this to happen. So what was basically happening is, initially you had a tennis ball that was hit with a racket. So initial velocity was 0, and after the hit the ball reaches the final velocity which you found in the previous case. So what was the answer? That was 14.5 meters per second. So when the racket hits you, the ball reaches a speed of 14.5 meters per second. Now you have to figure out what will be the time taken in this transition to happen, and then we put this time in this value to get our force. Now see if you can figure that time. Read the question and see if you have any sort of hint. See, the hint is given to you in the graph, the time taken. Can you figure out the time taken using the graph?
So I can see that it starts like the actual graph starts increasing at probably 13 seconds and starts and like gets to its lowest at around 26, 27, I suppose,
Okay, so let's say
and
at
it
it 13
hits its
and
highest at
26.
20.
Alright, so
Yeah,
13 and 26 is fine. Now if you subtract this, what will you get?
you get that to be 13.
Yes, so 13, and what will be the unit of this 13?
It'll just be seconds, right?
It's not seconds,
Meters, milliseconds,
milliseconds.
milliseconds.
So which means the time taken is 13 milliseconds. So now if I put this time in the formula, we write 0.84 divided by 13 milliseconds. Now we need to convert the milliseconds into seconds, so we have to write 10 to the power of minus 3. So now solve for this and check what is the value of the force.
Is it 64.61?
Okay, so 64. So whatever it is, 64. So your calculator is saying 64, so that's fine, 64. So basically I checked the marking scheme. What they have done is they have taken the time as 16 milliseconds. So let us just check the value. Okay, so you took 13. So let's see. Let me observe the graph again. So you have to observe the graph carefully. So we have 10. See, this is 15. So this should be close to 13. That is fine. Then we have 21. This should be 25, and this should be close to around 27, isn't it?
Yeah, so
So if you subtract this, you are getting 14 milliseconds. So in the marking scheme, what they have done is, if let's say if the student puts time as 14 milliseconds all the way to 16 milliseconds, and 13 milliseconds also could be considered, like what we have done. So if you stick to this range, you will be getting the marks. Even 13 will end up with the same, with you will get the marks then as well. So the force is 64, and what is the unit of this, Sheldon?
it'll just be newtons, right? So
Absolutely, yes. Force is equal to 64 newtons. That is the answer to this question. Alright, so now we are left with one last question, C part, which is determine, with reference to the work done by the average force, the horizontal distance traveled by the ball while it was in contact with the racket. So which means you had a ball which was initially at 0 velocity. After a time t, let's say if I take 14 milliseconds, in that time the velocity reached is, what was the velocity, the final velocity? That was 14.5 meters per second, the final velocity of the ball, right? So
yeah,
14.5.
so
Now in this particular transition we have to figure out what is the displacement or the distance traveled by the ball. So this is your question. See if you can figure out the value of S. And also we have to remember that we have to whatever method we use, it has to incorporate the work done by the average force.
So isn't it just final minus initial?
Final minus initial is the change in the velocity. So there are two ways of solving this. Let's say if I use the equations of motions or the CUAT equations. So let's say if I use this, v is equal to u plus at, right? So the final velocity is 14.5, initial velocity is 0, time taken is, you have considered 14 milliseconds. Solve for the value of a. Tell me what will be the value of acceleration.
That'll be 1.035 meters
One point.
meters per second. Yeah. 1.035.
Okay, meters per second square. Now we have to find out the value of s. So we can use the second equation of motion, which is s is equal to ut plus half at square. Now see, initial velocity is 0, so this entire parameter vanishes. Now put the value of a as 1.035 and time will be your 14 milliseconds. Okay, by the way, Sheldon, the value of acceleration should not be 1.035. See, that is because if I divide 14.5 by 14 milliseconds, which is 14 into 10 to the power minus 3, I think you haven't put the 10 to the power minus 3 parameter. So just check if so, your value should be 1035 meters per second square.
Yes, I hadn't given the final
Yes, see.
um into 10 into minus 3.
Yes, so
Yeah.
eventually your acceleration will be 1035 and not 1.035. So put a as that value and time as 14 milliseconds and see what value of s you are getting. So this we need to find.
So I'm getting the displacement to be 0.101.
0.101.
Yes, sir.
And what will be the unit?
So I don't actually remember the unit for displacement.
The displacement is just meters. It is distance and displacement have the same unit. So 0.101 meters. Alright. So this is the way we solve this question. But if you scroll up, if we read the question again, part C, it says that determine with reference to the work done by the average force. So in the method which we have done, we have used the CUAT equations. We have not considered the work done by the average force. So now the method which you did, this is correct, just this is just for a conceptual clarity, but then we have to resolve now using the work done by the average force. So first of all, we have to find that value. What will be the total work done by the average force? So let me explain that. So Sheldon, do you remember the work energy principle which we had did in the class?
No, not really, sir.
Just it's okay, so we'll revise it. So the work energy principle states that the total work done, now sigma stands for summation, so sigma means total. So total work done is always equal to the change in the kinetic energy. So in this particular case, you had a ball which was initially at rest. A racket strikes the ball, it reaches a velocity of 14.5 meters per second in a span of time 14 milliseconds. So this is your motion which is going to happen. Now let's apply the work energy principle. So the work done will be the work done by that racket, or the force applied by the racket, and that will be equal to the change in the kinetic energy, which will be the final kinetic energy minus the initial kinetic energy, right?
Yes, sir.
Now what will, just tell me what will be the value of initial kinetic energy?
Half mv square, right? So it'll just be half into m being, wait, the mass is like 5.8 into 10 raised to power
Minus
negative
2.
3, if I'm not wrong.
It's
Minus 2, sorry.
Let me just
And
5.8 into 10
yep,
to the power minus 2. Yes. So what will be the initial kinetic energy? Half into
I think
m.
the initial will be 0, right?
Yes, see, initial velocity is 0, so the initial kinetic energy is 0. So now all you are left with kf, which is half into m into v square. See, mass is given to us as 5.8 into 10 to the power of minus 2, multiplied by, in place of final velocity we put 14.5, right? So
Yes, sir.
this is the total work done by the applied force, now using the work energy principle. Now solve for this and tell me what is the value.
I'm getting my answer to be 6.09.
Okay, 6.09, so let me just write it down. 6.09, and what will be the unit of work?
It'll be joules, right, sir?
Perfect, yes, that is joules. So we have found out the work done by the applied force, which is 6.90 joules. And we go back to the basic definition of work. Work is nothing but the product of force and displacement, right? This is the basic formula for work. Now let's go back to our question and see what were we supposed to find. So part C states that we have to determine the horizontal distance traveled by the ball while it was in contact with the racket, which means it is S, which is what we need to find, right? And in the previous part, part B, we had we had to find the average force exerted on the ball by the racket. So in your notebook, just check what was that value of the applied force which we had found out.
So your voice wasn't really clear. What was it supposed to do?
Okay. So did you understand till this point where we found 6.09 joules?
Yeah, so I got to that.
See, this
And
is
then
the
your voice kind of got cut.
okay, no issue. See, this is the work done, and the formula for work done is force multiplied by displacement, right?
Yeah, so
Now in this particular question, we have to find S, the value of the displacement. See, like in the previous method, we use S is equal to half AT square, and you eventually arrived at this answer, right? 0.101 meters. So
yes, sir.
this is what we are supposed to find. So if I take the force, let me write down the equation. Fs will be 6.09. So S can be written as 6.09 divided by the applied force. Now in the previous part, part B, we had found out the value of the force. So let me just scroll up. Let's see what was that value. Okay, so remember this, you had found out 664 newtons.
Yeah, so it's the average force
Now do
applied.
one thing, this put time as 14 milliseconds as not 13. 14 is closer. So now check what is the new value of the force. If my denominator is 14 milliseconds,
So it'll be 60 newtons.
60 newtons. Okay, so F is 60 newtons. So now if we put this value of 60 newtons into our formula, which is this 6.09 divided by 60. So tell me, what is this value?
Getting my answer to be 0.1015.
Yes, so 0.1015 meters. So now what we have done is we have used two methods to find out the displacement. In one case you are getting 0.1015, and in the first method you are also getting a similar answer. So that was 0.101, isn't it?
Yeah, so
So now both of these methods are fine, but in an exam scenario you have to use this second method, because it clearly states that we have to incorporate the work done by the applied force, right?
yeah, so
Okay, so have you written it down, the whole thing?
no, so not yet.
Okay, so then let's do one thing. Okay, so then finish it off, the whole writing down. Just let me know where to scroll up or down.
Yeah, so just scroll up, no? Yeah, it's about it. So can you scroll down just a little bit?
Okay.
Yeah, so can you scroll down just a little bit more?
Okay.
Yep, done, sir.
Okay, so we got 0.1015. Alright, so Sheldon, we did two questions today. So what we are going to do now is I'll send you the recording along with the notes. So please go through both the, so you have to solve both the questions again, go through the solution, write down your notes, and in the next class we'll do some more questions.
Alright, sir.
Alright, so
When
we
is
have,
the next class, by the way?
it's on Sunday, 1 p.m.
Alright, sir.
So we are having two classes per week. So Sunday is 1 p.m. and then this particular class Friday 4 to 6. All right,
Alright, sir.
chalo, take care, bye.
Yep. Thank you, sir. Bye, sir.